Let's look at magnetic force between two parallel current-carrying conductors, such as shown here. So you have two conductors, very long conductors, carrying current, say I1 for conductor number 1 and I2 for conductor number 2. And of course the distance between them is d. This is the case where the two currents are parallel to each other, but the two currents can also be opposite to each other. We want to see how magnetic force between these two parallel conductors arises, namely the origin of the magnetic force. Let's look at case number 1, where the two currents are parallel to each other. Now let's calculate the force on 2 due to conductor 1. The magnetic force the current I2 feels is a result of the magnetic field that I1 produces at the location of I2. The circle in yellow shows the magnetic field produced by current I1. The direction of current I1, namely upward, shows the direction of the magnetic field would be like that. This follows directly from the right-hand rule that we have discussed before. At the location of conductor 2, the direction of the magnetic field produced by current I1 would be going into the board, like that. So the magnitude of the magnetic field produced by conductor 1, or the current 1 flowing in conductor 1, is quite simply mu naught I1 over 2 pi d. So this is the strength of the magnetic field at that location. Now since current I2 is going that way, the magnetic field due to current I1 is going into the board, the direction of magnetic force experienced by this conductor 2 is given by the following expression that we have also covered. It's I2, the length vector of conductor 2, cross into the magnetic field produced by current I1. So the direction of vector L2 follows the direction of current I2, and the magnetic field due to current I1 is given by that. Making a cross product will give you the direction like that for the force on conductor 2. So conductor 2 would experience a magnetic force towards conductor 1, like that. Let's call it F2. Since the vector B1 and L1, note L1 is the length of conductor 2, and the direction of the length vector L2 follows the direction of the current I2. So the direction of the current I2 and the magnetic field B1 are perpendicular to each other. The magnetic force F2, namely the magnetic force on conductor 2 due to conductor 1, will simply become I2 L2 B1. B1 is given by mu naught, that is this expression right there, I1 over 2 pi d. Now, since L2 is very long, it's a very large number, it's more convenient to talk about force on conductor 2 per unit length. So let's call that little f2, and that is defined as capital F2 over the length L2. And that simply is going to be mu naught I1 I2 over 2 pi d. So this is the expression for magnetic force per unit length on conductor 2 due to conductor 1. We see in this case where the two currents are parallel to each other, conductor 2 is attracted to conductor 1, namely the force is going towards conductor 1. Now let's look at the force on conductor 1 due to the magnetic field produced by conductor 2. The magnetic field produced by conductor 2, or the current I2, at the location of conductor 1 will look something like this. We note the direction of the magnetic field. Let's call now this magnetic field B2. It's going in that direction, again following the right-hand rule. At the location where the conductor 1 is located, the magnetic field will be coming out of the board, like that. So the current I1 is going up, the magnetic field is coming out of the board, like that. So that is B2. So the direction of magnetic force that I1, or the conductor 1, experiences would be following the following equation. I1 L1 cross into B2. So the force conductor 1 experiences is due to magnetic field produced by conductor 2, or the current 2. The direction of vector L1 is the same as the direction of the current I1. So making the cross product between I1 and B2 would give you a direction of magnetic force going like that. So this is the direction of magnetic force on conductor 1. Let's call it F1. So it's going to go like that. So that is the expression for the force F1. We note vector L1 has a length L1, it's very long, and the direction of vector L1 is the same as the direction of the current I1. The direction of I1 and B2 are mutually perpendicular to each other, so we can write an expression of the magnitude for F1 as quite simply I1 L1 B2, because the angle between I1 and B2 is 90 degrees, sine 90 is 1, where B2 is quite simply mu naught I2 over 2 pi d. Substituting this expression in that, we get I1 L1 mu naught I2 over 2 pi d. So since we'll be interested in the force per unit length on conductor 1, let's call it little f1, which is defined as capital F1 over L1. The expression for it is mu naught I1 I2 over 2 pi d, the same as the force per unit length on conductor 2. And the direction of F1 now is towards conductor 2. And you see clearly that the two wires attract each other when the current within them is parallel to each other. So the force is attractive in nature. What happens if the currents are opposite to each other, they're anti-parallel to each other? Let's first calculate the force on conductor 2, and it follows the expression: the current on conductor 2, the length of conductor 2, the length vector that is, cross the magnetic field produced by current 1 at conductor 2. As before, the magnetic field due to current I1 will be going in that direction, so at conductor 2 it's going into the board. However, note that now the current I2 is going down like that, so that is I2, and the magnetic field is going into the board. So these two vectors are perpendicular to each other. Note that the vector L2 has the same direction as the direction of current I2. Making the cross product of these two vectors will result in a force F2 going to the right. So that is the force on conductor 2, which is just that. The magnitude of magnetic force on conductor 2 is given by I2 L2 B1. But we already know what B1 is. It is mu naught I1 over 2 pi d, namely the magnetic field created by current I1. Substituting B1 into this expression, we get F2 to be I2 L2 mu naught I1 over 2 pi d. The force per unit length at conductor 2 due to conductor 1 is given by capital F2 over L2, which will result in the expression mu naught I1 I2 over 2 pi d. Note the direction of the magnetic force on current 2 due to current 1 is now heading away from conductor 1. So it's as if it's being repelled to the right. By now it should be clear that the direction of force on conductor 1 due to magnetic field of conductor 2, which goes like that, and at that location it's going into the board like that, would be going that way. Let's see if that is indeed the case. So the current I1 is heading up, the magnetic field is going into the board. By crossing L1 into B2, so that cross is B2, and vector L1 follows the direction of I1. L1 is the length of this conductor 1. You see that direction of F1 indeed goes to the left. The expression for F1 is the same as the direction for F2. It's given by mu naught I1 I2 L1 over 2 pi d. The only difference now is the direction of F1. F2 was going that way in our previous analysis, and F1 it's going to the left, signifying that the force is repulsion in nature. So they repel each other when the direction of the current are opposite to each other. Let's look at the following problem. Two long parallel wires are separated by a distance 20 cm, 0.2 meter. The force per unit length on each wire exerts on the other is 8 times 10 to the power minus 5 Newton per meter. Note the unit. This is not force, it's force per unit length, that little f that we talked about in our previous slide. The wires repel each other. Now what that means is the two currents must be opposite to each other, as we have discussed a few minutes ago. Only then they can repel. If one current is a 4 ampere, what is the other current? Namely, what is this? I. The expression for force per unit length is given by mu naught, the product of the two currents, over 2 pi, the distance. We know what the force per unit length is. It's 8 times 10 to the power minus 5. Mu naught is a constant, 4 pi times 10 to the power minus 7. I1, let's take 4 ampere to be I1, and I2 is the unknown I. Divide by 2 pi, distance between the two wires is 0.2 meter, or 20 cm. And we can solve for the current I. And when you solve for it, you will get 20 ampere. And that solves the problem. Thanks for watching.